Morning students, let us start with today's class on the topic structure of atom. In our previous class, we had discussed about fillings of orbitals in atoms, how electrons are filled in the different orbitals. And now we had also discussed about the energy level diagram of different orbitals, their energy level. We had discussed about Aufbau principle and Pauli exclusion principle. So today we are going to discuss about Hund's rule of maximum multiplicity, electronic configuration of atoms from atomic number 1 to 30. You are able to, after learning the electronic configuration from 1 to 30, you are able to write down the electronic configuration of the rest of the all elements which are present in periodic table, or later on we will discuss those as well. And we will also discuss some exceptional configurations, their stability of completely filled and exactly half filled orbitals. So let us begin. So Hund's rule of maximum multiplicity. This rule deals with the filling of electrons into degenerate. You are knowing the meaning of degenerate, that is equal energy. Degenerate orbitals of the same subshell, PDF. So according to this rule, what we can say that electron pairing in PD and F orbitals cannot occur until each orbital of a given subshell contains one electron each or is singly occupied. Here S is not been taken into consideration because we are knowing that S is having only one orbitals. So obviously the electrons will fill only in that very orbital, but in P we are having 3 and in D we are having 5 and in F we are having 7. So that's why according to this rule, electron pairing in P, D and F orbitals cannot occur until each orbital of the given subshell contains one electron each, or as we can say singly occupied. Now this is due to the fact that electrons being identical in charge repel each other when present in same orbital. So this repulsion can however be minimized if two electrons move as far apart as possible by occupying different degenerate orbitals. So further we can say that all the singly occupied orbitals will have parallel spin, that is in the same direction, either clockwise or anti-clockwise. And this is due to the fact that two electrons with parallel spins, of course in different orbitals, will encounter less inter-electronic repulsion in space than when they have opposite spins while staying in different orbitals. So let us consider, for example, for the element nitrogen, which is containing 7 electrons. So its configuration can be written as like one s orbital. In one s orbital it is having 2 electrons. You can see over here one arrow is upside and another arrow is downwards. Similarly in 2s orbitals as well, 2 electrons are there, one is upward, one is downward. Again in 2p orbitals we are knowing that it is having 2px, 2py, 2pz. So we are having already completed fill 4 electrons. Now we are having left with 3 more electrons. So 3 more electrons, how we are able to fill it? By putting one electron first in every orbitals, because we in the second one just below it you can see that 2 electrons are filled in the first orbitals of p subshell, and that is incorrect. This putting of electron in this same orbital is incorrect, because just now according to Hund's rule we have discussed that until each orbital of a given subshell contains one electron, or each of the orbital of the given subshell is singly filled, singly occupied, only then we are able to put another electron to get it paired. So that's why we can say that for the first, what the correct one, what will be the total spin? The total spin of the unpaired electrons. So unpaired electrons, you can see over here the electrons which are not being paired up. So the total spin of the unpaired electrons will be one half, half plus half plus half. That will be equals to 1 by 2, or in mixed fraction, or you can say 3 by 2. So that will be the total spin of the unpaired electrons. So this is one of the example of Hund's rule. So in accordance with the Hund's rule, we are knowing that the above configuration is the correct first one, in which the three unpaired electrons occupying 2px, 2py and 2pz orbitals, and they have parallel spins, either all are here or all are clockwise, so is correct. And while the below is incorrect. Why below is incorrect? Because pairing of electrons has been shown in 2px orbital, and we are knowing that, and it is been paired without putting the third electron in 2pz orbital, which is also not according to the Hund's rule of maximum multiplicity. So that's why this example properly illustrates the Hund's rule. So let us discuss more about the calculation of number of unpaired electrons. Just now we have discussed what are the unpaired electrons. So these examples are also in accordance with the Hund's rule. Like for hydrogen, it is containing only one electron. So in 1s subshell, it is having one electron. So it's correct, configuration is correct. And number of unpaired electrons, so obviously it is having only one. So in that very subshell, one electron is there. So number of unpaired electron is 1. Again, for coming to helium, it is containing 2 electrons. So first of all, 1s orbital will be filled up first, because the energy of 1s and 2s both are different. 2s is having slightly higher energy. So according to Hund's rule, the 2 electrons first goes to 1s, and then after both means 1s is already paired up. Subshell is already paired up with electrons, so no unpaired electrons. So similarly, there are many more examples. Like for suppose consider us nitrogen. Just now we had discussed for oxygen. It is containing 8 electrons. So for 8 electrons, for suppose we are considering 1s subshell. So in 1s we have to fill first 2 electrons. Again for 2s we have to fill 2 electrons, because we are knowing that 1s, 2s and 2p, these all three subshells having different energies. So we are going to fill according to Hund's rule. So 1s is properly filled, 2s is filled, and after that we will come to 2p. And in 2p we are having left with 4 more electrons, and already we are knowing p orbitals having 3 orbitals. So initially we have to fill one electron to each one of them, and then after filling one, then we start pairing up. So 2px is already paired up, but 2py and 2pz is containing one single electron. So the number of unpaired electron is 2. I hope you have understood how to calculate the number of unpaired electrons. So this is about Hund's rule of maximum multiplicity. So now the next topic is electronic configuration of atoms. So let us discuss how we are able to write down the exact electronic configuration of different elements. So the distribution of electrons in different cells, subshells and orbitals of an atom is called its electronic configuration. So keeping in view the above rules, the representing an orbital by a box and an electron with its direction of spin by an arrow, the electronic configuration of the atom of any element can be represented like NLX, where N is the number of main or principal shell, and L is the symbol of subshell or orbital S, P, D or either F, and X is the number of electrons present in that very orbital. So for example, suppose if we are writing 4p1, that means it means that p subshell of the fourth main shell contains one electron. So to get the complete electronic configuration of any atom, a number of such notations are written one after the another, and we are knowing how they are being written in order of their increasing energies, which we had already discussed in Aufbau principle of the orbital, starting always with the orbital of lowest energy, that is 1s. We will first write 1s and then after that we will increase on. So let us discuss some examples. So you can see over here the electronic configuration, how we are able to write down the perfect electronic configuration. So for hydrogen, how we are able to write it down? We are knowing the notation NLX. So here N, hydrogen containing atomic number 1. So we can directly write the electronic configuration of hydrogen is 1s1. 1 is the total number of electrons present in that very element. So hydrogen containing 1 electron, so it is containing 1s1 is the configuration. For helium's 1s2, because it is containing 2 electrons, and we are knowing 1s, a maximum number of electrons it can hold is 2. So we should fill 2 electrons in it. After that, lithium is total having 3 electrons. So first of all, after 1s, what will be the subshell which is coming, which is having slightly higher energy than 1s is 2s, according to our principle. So again we have taken 1s and 2s subshell. So 1s we have completely filled 2, and after that we are leaving with 1 electron. So we are keeping that electron in 2s subshell. So 1s2, 2s1 will be the configuration of lithium. Similarly, for carbon, it is having 6 electrons. So if it is having 6 electrons, so after 2s, what will be the next subshell which is in slightly higher energy than 2s, that is 2p. So we are writing 2p after that, means after filling up 1s and 2s orbital, we are left with 2 more electrons, because it is 1s containing 2 electrons, 2s containing 4. So 2 more electrons will be filled up in p subshell. So and p subshell is having 3 orbitals, px, py, pz. So how to write down the orbital diagram, you are knowing, just now we have discussed how to write down it. Px will contain 1 and then py will contain 1, but for configuration directly we can write 2p2. It means p subshell is containing 2 electrons. So total configuration is 1s2, 2s2 and 2p2. So similarly, there are certain more configurations from 1 to 18 are given over here. So using this very configuration, you can write the electronic configuration of the whole of the periodic table. So according to, but you have to keep in mind that you have to select, like for example sulfur, it is containing 16 electrons. So 16 electrons means initially 1s filled, after 1s 2s will be filled up, after 2s 2p, and after 2s the next higher energy will be 3s, and after 3s 3p. So similarly it goes on, and then we have to fill up the number of electrons. So while filling up the number of electrons, there are certain other ways to write down the electronic configuration of these elements. So let us discuss that. That on the basis of noble gas configuration, we can also write the electronic configuration of elements using noble gases configuration. So what are noble gases? First of all of you are knowing that noble gases: helium, neon, helium atomic number 2, neon 10, argon 18, krypton 36, xenon 54, radon 86. So these are the noble gases, or these are also known as inert gases, because these are highly unreactive in the nature. So using these very noble gases, we can also write configuration. Like see, let us see the first example given over here. So first one is neon. For if we want to write the configuration, electronic configuration of neon in terms of SPDF notation, we can simply write 1s2, that is containing 10 electrons. So 1s2, 2s2 and 2p6. So 10 electrons fulfilled. But if we want to write it, the configuration in terms of noble gas notation, how we have to write this? Just simply have to put the big bracket, and inside it we have to write neon, because neon is already the element which is containing 10 electrons. So for better understanding, let us take another example, sodium. For sodium, if you've been asked to write down the electronic configuration, you are able to write it down? Yes, because 11 electrons are total in sodium. So 1s2, 2s2, 2p6 and then 3s1. So for writing in terms of noble gas notation, how we have to write for sodium? For writing sodium configuration, we have to first write again inside the brick bracket, we have to write neon, and after neon we have to write only 3s1, because we are knowing that neon is already containing 10 electrons, means its configuration is already there. So we need not to write the configuration of neon. We just simply write, in place of that very configuration, we can simply write neon in big bracket and then 3s1. So similarly proceeding towards magnesium, neon in brick bracket 3s2, and further moving on up to chlorine. So up to chlorine, it is we have to write inside the brick bracket neon, because after chlorine is having 17 electrons, after chlorine argon 18 electrons, and we are already having a noble gas which is containing 18 electrons. So starting from argon, we have to start writing argon in big bracket. So after argon, suppose we have to write configuration for potassium. So potassium having 19 electrons. So basic electronic configuration you are knowing, SPDF notation. After writing SPDF notation, we can also write in terms of noble gas notation, that is argon in big bracket and then 4s1. Because the configuration of argon we are knowing, it is containing 18 electrons, and after 18 electrons, the 19th electron will move to which subshell? That is 4s1. 4s subshell it will goes to. So that's why its configuration is written as argon 4s1. Similarly, for proceeding towards calcium, it is also written argon 4s2. Similarly, we can move further, like up to 30 or up to 35 we can use argon for writing the configuration. Up to 35 atomic number we can use argon, because after 35, 36 will be the krypton. 36 is the krypton, atomic number of krypton, the next noble gas. And if we have to write the electronic configuration of 37 atomic number, that is rubidium, so we have to write in big bracket krypton Kr, and after that the 37th electron will move to 5s orbital, that is 5s1. So Kr 5s1. So so on. So using this very manner as well, we can write the configuration of the elements, and this configuration is known as noble gas notation. And the previous one which we had discussed is the SPDF notation. So I hope it's clear to all of you. For getting it more clear, you have to practice it at your home, so that you are able to understand it properly. You are able to write the electronic configuration by your own of every element. So now there are some exceptional configurations. There are many exceptional configuration throughout the periodic table, but there are certain exceptional configuration between 1 to 30. So let us discuss those exceptions configuration.
Going to talk about the exceptions in the electron configuration. Two of the main exceptions you need to know are for the elements chromium and copper. Chromium has an atomic number of 24, so we're going to use the information on the right to write the electron configuration for chromium. So we're going to write it until the exponents add to 24. So we're going to start with 1s. S always carries 2 electrons. After that, the next one is 2s. So that's 2s2. Then after 2s comes 2p. The p sublevel has 6 electrons. And then we have 3s, which is 2 electrons. After 3s we have 3p, 3p6, and then 4s2. After 4s, then we have the 3d level, 3d4. Notice that the exponents, they add to 24. However, the last part, the 4s2, 3d4, that part is going to change for chromium. let's draw it out. So here's the 4s orbital, and here is the 3d orbital. Now instead of being 4s, 2, 3d, 4, which looks like this, we're going to get 4s, 1, 3d, 5. The reason for that is electrons, they prefer to be unpaired versus paired, and so that unpaired electron, which was here before, it sees this empty space, and so it decides to jump here. So the configuration for chromium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Now, copper is very similar. Instead of copper being 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9, one of the s electrons jump into the 3d sublevel. So it's going to be 4s1, 3d10. Now this trend, it works also for elements in the same row as chromium and copper. For example, molybdenum behaves in a similar way as copper does, chromium. Molybdenum is right below chromium, but for some reason tungsten doesn't do it. Now, the elements under copper.
I hope students you have understood the exceptions for chromium and copper. You must have seen that for chromium the configuration should be 4s1 3d5 instead of 4s2 3d4, and for copper it should be 4s1 3d10. So why these electrons are moving towards the d orbital from s? Because we are knowing that the stability of completely filled and exactly half filled orbitals. So let us discuss that one. So why this is so? This is because of the following two reasons. Like for first one is symmetrical distribution. So symmetrical distribution, it is well known fact that symmetry leads to stability. So thus the electronic configurations in which all the orbitals of the same subshells are either completely filled or are exactly half filled are more stable because of the symmetrical distribution of electrons. Just now we have discussed about the chromium. Like initially for chromium you have seen that it is 4s2 3d4. So 4s2 it is having 2 electrons and 3d having 4 electrons. So in order of their stability, to gain stability, the one of the 4s electron is being jumped over to the 3d orbitals, the fifth orbital of the 3d subshell. So there, after shifting over there, the configuration is 4s1 3d5. So initially chromium has configuration 4s2 3d4, so it is not stable. So in order to gain stability and in order to gain a symmetrical distribution of electrons, the 4s electron is shifted to 3d orbitals. So we are getting 4s1 3d5. So in terms of noble gas configuration also, we can write the electronic configuration of chromium like argon 4s1 3d5. This is one of the reason. In order to achieve symmetry, the electrons are shifting from one orbital to another orbital, and because of the symmetrical distribution which is leading to the extra stability of the orbital. So ultimately all these electrons are shifting towards another orbitals because in order to gain stability, in order to gain symmetry. So one more reason is there, that is exchange energy. So what is exchange energy? The electrons with parallel spins present in the degenerate orbitals tend to exchange their positions. So means the electrons which are only including with parallel spins, means if one electron is of clockwise, then it will exchange only with the another electron which is also in clockwise direction. So the energy released during this exchange is called exchange energy. So the number of exchanges that can take place is maximum when the degenerate orbitals are exactly half filled or completely filled. As a result, the exchange energy is maximum and so is the stability. Why it has been said that the number of exchanges that can take place is maximum when the degenerate orbitals are exactly half filled or completely filled? Because suppose if we are considering D5 configuration. So for D5 configuration, we are knowing it as D5 means D orbitals, orbitals having 5 orbitals containing one singly occupied electrons, and all are in the upside manner, means all are having spin quantum number plus half. So the first electron if we are considering, so it can exchange its position by the rest of the 4. So means 4 exchanges for 1 electron. If we are considering the second electron, then it can exchange its positions by the rest of the 3 electrons, means the electron number 3rd, 4th and 5th. So 3 exchanges with the second electron. And if we are considering the third electron, so it can exchange its position with the 4th and 5th. So 2 exchanges with the third electron. And if we are considering the 4th electron, then it can exchange its position only with the 5th one. So one more exchange is there. So the total exchanges is 10. 4 plus 3 plus 2 plus 1, that is 10. And if the same, if we are going to calculate the number of exchanges for D4, then it will come 6. So that's why it has been said that the number of exchanges that can take place is maximum when the orbitals are exactly half filled or completely filled, and D5 is the half filled configuration. And as the exchange energy is maximum, so the stability is maximum. So I hope you have understood it properly. So today we have discussed about Hund's rule of maximum multiplicity, electronic configuration of certain elements from 1 to 30, and exceptional configuration in between to 1 to 30, and their stability of completely and half filled electrons. If those who have not understood properly, try to practice it at your home for understanding. So thank you students.